I'd like to thank the organizers, in particular Andrew, for the opportunity to speak to you all today. And for me, it's an unusual circumstance to be opening a conference like this. And it's the first time I've been at one of these differential geometry conferences, and it's a pleasure to have that so many of you have appeared. So before I start, let me just try to give a quick 2-minute summary of what I want to tell you about, and then I'll actually start the talk. So I want to think about a hypersurface in flat affine space, and it acquires some geometric structure. One can summarize that geometric structure, if the hypersurface is non-degenerate, as a pair of conjugate special statistical structures, for instance, is one way to say it. And what I want to do is treat such geometric structures as generalizations, analogs of Riemannian, pseudo-Riemannian metrics, and analyze to some extent the picture that corresponds to constant sectional curvature Einstein equations, scalar curvature in this context. And so where do affine spheres and Griess algebras come in? The Einstein equations I'm going to discuss, when you consider them for a hypersurface in flat affine space, they describe exactly the so-called affine spheres. And when you look for solutions that don't arise in this way, it leads, one way to construct some is via a certain class of commutative non-associative algebras. It includes the Griess algebras. So, and I'm saying Griess because my understanding is that Robert Griess pronounces his name that way. If you've never heard of affine spheres, Griess algebras is not important. I'll get to both of them in the second half of the talk. At first, I'm going to start with something more basic, and hopefully it will. So the thing that I need to explain to begin is that somehow it's going to turn out that the equations I want to look at can also be thought of as Einstein kinds of equations for a metric coupled to a cubic symmetric tensor. And so I want to start by speaking about how to couple a tensor to a metric. And for some of you, this will probably be relatively familiar. So here everything on this slide should be well known to everybody. So when we look at a metric in this talk, all metrics can have an arbitrary signature. We usually organize our thinking about them in terms of a hierarchy of curvature conditions: constant sectional curvature, Einstein, and constant scalar curvature. And I sort of think of each of these successively weaker conditions as a trace of the previous ones. Probably a better way to think about it is you decompose the curvature tensor into its irreducible constituents, and you require that one or the other is null or parallel, something along these lines. I'm going to use this notation repeatedly on slides, this Kulkarni Nomitsu square of the metric. It's simply the curvature tensor determined by the metric, and I wouldn't worry about coefficients and sign conventions. I would just think of it that way. And likewise, I'll write rho of a tensor to mean it's Ricci trace, and I trace on certain indices, but sign conventions, of course, are always a bit of a pain. My sign convention is such that with this minus sign, this has constant sectional curvature kappa. So the two things I want to comment here are there's sort of two ways of thinking about the Einstein equation. There's the geometer's way of thinking about it, which is the vanishing of the trace-free part of the Ricci tensor, which of course implies constant scalar curvature when you trace the differential Bianchi identity. And the other way of thinking about it is the more physical one, which is written in terms of the divergence-free part of the Ricci tensor, which is usually called the Einstein tensor, which is this form. And here, when one writes it in this form, then the scalar curvature term, one thinks of it as a cosmological constant. And here you're thinking of a vanishing stress energy tensor. So it's basically vacuum Einstein equations with a cosmological constant. The other comment I want to make is I want to think in this talk, I want to think of constant sectional curvature as projective flatness of the connection, of the Levi-Civita connection to the metric. So that's justified by the classical Beltrami theorem, which tells me that a pseudo-Riemannian metric has constant sectional curvature if and only if its Levi-Civita connection is projectively flat. And I'll just remind you what projectively flat means. I consider two torsion-free connections to be projectively equivalent if the traces of their geodesics are the same, the images of their geodesics, and then it's projectively flat if locally I can choose charts in which the traces of the geodesics are straight lines. And it's a classical fact that this is equivalent to the vanishing of a certain part of the curvature tensor, usually called the projective Weyl tensor, which is the trace-free part of the curvature where you're taking traces just using endomorphisms and there's no metric present. And of course, in dimension 2, one has to make special considerations. And that's true for everything I'll say in the talk, and I won't generally mention them. Okay, so the next slide is I want to speak about how to couple these sorts of equations, how to write a parallel equations, but where I add a tensor with certain symmetries. And so the model is the Einstein-Maxwell equations. And so just let me remind you how this goes. You have a two-form, which you think of as the electromagnetic two-form. And here you have various quadratic expressions in the, I don't see the dot. This is just the composition of F with itself as an endomorphism up to sine. And this is its norm. I'll write the norm of F squared, even though my metric might have signature, indefinite signature. And so here I've written the equations in two ways. The more different, this is the differential geometric way of writing it. This is the physical way of writing it. You suppose that the form is closed and it's co-closed, which means there are no sources. And here you have a stress energy tensor, and this tensor is cooked up so that these two equations imply that this tensor is divergence free, which is what matters. And so really probably the easiest way to think about it here is we have the Einstein tensor plus a cosmological term is equal to the stress energy tensor. This and this are divergence free. That implies this is constant, and it has this expression in terms of the scalar curvature and the norm squared of the two form. So the first thing I just want to explain is there some analog of this top line that makes sense, at least in this context? So there is, and here I've written it for a general P form rather than just a two form because it's just as easy. So here I have a P form, and the capital A is just accumulating P minus 2 of the indices. I have a quadratic expression in the form. It doesn't matter what all this complicated thing means. It means skew symmetrization over I and J, but this is a tensor with the symmetries of a curvature tensor. That's the point. So this is a quadratic map associating to a form, something in the symmetries of a curvature tensor. This is its Ricci trace, which, well, you can almost see that it's the same form as what was on the previous slide here. It just has some extra indices over which you're tracing. And so here's the stress energy tensor. So it looks just like on the previous slide. The only change is there's a P here. It satisfies this identity. So one can find this written in a paper by Baird about 15 years ago. The point of this identity is simply that if the form is closed and co-closed, then this tensor is divergence free. And so then here are this is the analog of the hierarchy of equations simply for a metric. Here we have a curvature term equal to a multiple of the metric. And then here we have the Einstein-Maxwell equations. And then here we have what would be the analog of constancy of scalar curvature. Here I've inserted something which wasn't present before, which is this epsilon, which is going to be plus or minus 1. From a physical perspective, only one choice is meaningful, but from a differential geometric perspective, both choices are meaningful. And in general, the behavior of the solutions to equations like this will depend quite strongly on the sign of this epsilon. I'm making it plus or minus 1 because I can always rescale F because this is quadratic. I can make a constant here 1 or minus 1 if it's non-zero. So that it's really only the sign that matters here. Okay. So, and I'll show some examples in a minute, but what I want to explain now is there's a completely general setup here. So I want to think, I want to think of a space of tensors with determined symmetries corresponding to some Young diagram, the trace-free tensors with the symmetries codified by a certain Young diagram. So forms would, P forms would correspond to a Young diagram that's just a vertical row of boxes, completely symmetric tensors to a horizontal row of boxes. And so the more formally, I want to think of an irreducible SON module. And then I have the associated bundle of the frame bundle, which of my smooth manifold. That's a way of describing such. So this includes spinor bundles, if you like, too. And I'm going to write K here for the module of curvature tensors. And I want to start with the data of a symmetric module map from my space of tensors to the curvature tensor. So here one should be thinking of this map right here. Okay, for instance, and we'll see another example in a moment. But I suppose, so in general, for a general W, such a map need not exist, need not be unique up to scale. There can be more than one of them, but we pick one. And I'm going to normalize it so that its scalar trace, the trace of its Ricci trace is just the norm squared of the tensor. And so I'll define a stress energy tensor. It's always going to have this form. Here R is some number, which actually in all the cases I'll show will be an integer that depends on the representation theoretic data that defines this guy. So this was a minus P in the previous slide. And I need an operator that's going to function like the differential here, like a gradient. And so I'm going to just, let's call that A. So I've called it a generalized gradient. So this is in the sense of Branson. One takes one has this a tensor with certain symmetries. One takes its covariant derivative. And in general, one can decompose that by symmetries. And if you think about that, that's like tensoring W with the dual of the standard representation and then decomposing into irreducibles. The irreducibles, which appear in the case of SON, appear always with multiplicity 1, and I have projections onto each one of them. I compose that projection, and I get different operators here. And we'll see an example in a moment for symmetric tensors. And these operators act like, yeah, so they act a bit like gradients. And so I need to have an identity like this where general beta and gamma depend on again on the representation theoretic data. And if I do, then well, when A of omega and A star of omega are 0, this stress energy tensor will be divergence free. So there's some relation between R, beta, and gamma in general. They're not things I can choose. They're things that are determined by the data. And in all the examples I described, this is just the divergence up to sign. And so then the general scheme of equations I want to consider is exactly as on the previous slide, simply with these general operators in place of the specific tensors. And as to say, it's in place of D and D star, I have A and A star. This part is exactly the same. This part, everything else is exactly the same, except here I use this quadratic map, and here I use the stress energy tensor that's appropriate to the situation. Okay, so this is, so in general, this is quite general, and it's obviously an issue whether there even exists solutions to such equations. So let me just give the example, which is going to form the main focus of this talk. Which are Codazzi and Killing tensors. So here I'm thinking of a completely symmetric trace-free tensor. So from a representation theoretic point of view, that's a horizontal row of boxes. And so when I apply a covariant derivative to it, it's like I can add a box on the end or I can add a box below. And those correspond to two different generalized gradients, which are these operators here. The Codazzi tensor and the Killing one. The Killing one is just taking the completely symmetric part of the covariant derivative, and the Codazzi one is skew symmetrizing over a pair of indices. So this one corresponds to sticking a box below, adding a row, and this one corresponds to lengthening the row. My quadratic map in this case is up to some choice of constant here, is the Kulkarni-Numitsu square of the tensor. So again, A is all the indices that aren't mattering and are just being traced. And then this is the Ricci trace, which has exactly the same form as it did for differential forms. And for both of these operators, the adjoint suitably interpreted as essentially the divergence. And we have an identity just like on the previous page, where the stress energy tensors, the only thing to remark here is that in one case I have a K present, whereas here I don't have a K present. And somehow the sign and the K or not K depend on whether I'm increasing the number of rows or increasing the number of columns. And I don't want to go into more detail there, but people who are familiar with these sorts of general things probably can guess the general pattern here. So this is the setup, and then this is how the equations look. And what I want to emphasize is this is exactly the same slide as before, just a couple of notations have changed. There's nothing to understand. Here I'm writing it for I wrote it with the Codazzi operator. I could have written it with the Killing operator, which I called L, because the Codazzi case is the one I'm going to focus on. And maybe the only thing that's worth noting is that the final constancy of this cosmological constant condition behaves a little bit differently, in the sense that in the Codazzi case, it implies that this kappa that appears here is actually constant. That's not the case in the Killing case. And in general, this coefficient here depends on, in the same way as everything else on the representation theoretic data. Okay, so let's see some examples where at least something. So from now on, I'm going to focus on the Codazzi case. And so the simplest examples are hopefully familiar. The first one, the summary is this: that for a mean curvature 0 non-degenerate hypersurface in a pseudo-Riemannian space form, the metric and the second fundamental form are coupled projectively flat in this sense. They solve this equation here, which is the statement that they satisfy this well, with some choice of epsilon. They satisfy this equation, and the second fundamental form satisfies these first order differential equations. So that's just the Gauss-Codazzi equations. So here, just to make it clear, this is what I mean by constant sectional curvature. Non-degeneracy, just my metric could have a signature, so it could be indefinite signature, and so I need to suppose that it restricts to an actual metric on the hypersurface. And epsilon is determined by, I pick a unimodular normal, and then epsilon is determined by its sign, and actually epsilon is minus the sign of the metric evaluated on this normal. And then this fits neatly into this picture. And what one finds is that in general, the Gauss-Codazzi equations look like this, so that if the second fundamental form is actually trace free, this vanishes, and you actually get a solution to the equations on the previous page. Let's see an example for cubic tensors. So it's exactly the same structurally. It's just now my ambient space is here. It can be a Kähler manifold, a para-Kähler manifold, pseudo-Kähler manifold. Basically, that means I have a metric and a almost complex structure, almost para-complex structure. So epsilon is -1 in the Kähler or pseudo-Kähler case. It's +1 in the para-Kähler case. I have the associated Kähler form. That it have constant holomorphic curvature for C, or holomorphic in whatever appropriate sense, means in my notations that the curvature tensor has this expression. Here, this is the same dot operation I saw before on forms, and this is the same Kulkarni-Umitsu product as before. I suppose that I have a non-degenerate submanifold, meaning the metric is non-degenerate, and I suppose it's Lagrangian with respect to the symplectic structure. And then this 3 form is essentially the second fundamental form. X, Y, and Z are tangent vectors, but it's twisted in a sense by J. So that's how to think of this expression, because this is G with J interior multiplied. So you can think of this that way. And the point is, this is completely symmetric, and its trace is this one form. This one form is not dual actually to the mean curvature one form. It's dual to J times J applied to the mean curvature vector field. But this is, if you've seen these things before, this is completely standard. And these also satisfy the Gauss-Codazzi equations look like this. Here, epsilon is this epsilon that shows up here. So it depends strongly on whether I'm in a Kähler or para-Kähler, behaves very differently. And again, if the mean curvature is 0, then I get a solution to these equations here. Okay. So I think of these as projectively flat equations somehow. So this is the summary. For a mean curvature 0 non-degenerate Lagrangian immersion in whatever type of Kähler manifold of constant, whatever type of holomorphic sectional curvature, this pair solves these couple projectively flat equations. So there are examples. I should comment that this example is essentially the same example in the para-Kähler case as the affine sphere, the affine hypersurface example I'll talk about in a little bit. Locally, they're equivalent. Just to see that there are, I want to give an example of something that solves these Einstein equations without solving these stronger equations. So here's the simplest one I know. Take a compact connected simple Lie group, so SON, SUN, something like this, with the biinvariant metric, which is given by the negative of the Killing form. And we take a harmonic, homogeneous, degree K invariant polynomial. There's an O that shouldn't be here. And so this is its complete polarization, which is just a tensor. So I'm not going to give explicit examples, but it's such that such polynomials are completely understood. And so one can write them all down in principle. And then the pair, this metric plus this tensor solves these coupled Einstein equations, but in general, it won't solve the couple projectively flat equations. And the proof that this solves these equations is very simple. Basically, the summary is that the G invariance decouples the equations. So this metric is already Einstein in its own right. And the Ricci trace of the Kulkarni-Numitsu product of this tensor with itself is G invariant. G invariant two forms have to be multiples of H. And so both this and the Ricci tensor of H are multiples of H. And so their linear combinations are multiples of H, and that's what I need. The point is the G invariance of the polynomial implies that this polarization is necessarily parallel, and so in fact it's Codazzi as well. Anyway, it's just the point is not to understand the example so much as that there is an example. So let me just, there are going to be two slides here where I state some general properties of solutions to the couple projectively flat equations to observe that they recover some well-known theorems in classical cases. But there's a general scheme here, and I just want to quickly explain it. I'm not going to say anything in detail. So there's a number of questions. First of all, if I have tensors solving these equations here, there's a question of whether such tensors even exist. And so at least obstructions to their existence are given by vanishing theorems. So for K forms, this is just Hodge theory. And for Codazzi tensors and Killing tensors, the two examples I was talking about, there are a number of papers that give essentially the definitive, the best results possible. So for Codazzi tensors, it's in the case of valence 2, it goes back to an old paper of Berger and Evan, and then Stepanov wrote a paper in the early 90s, and then actually in recent years with collaborators, he's written some more refined papers. And then in the Killing case, or the more general case of conformal Killing tensors, there's a paper of Dairbekov and Sharafutnov, which uses integral geometry techniques. And then there's a more recent paper of Heil, Semel, and Moriano, which uses exactly the sort of representation theoretic machinery I was discussing before, and it's a very nice paper. And there's a little note of Hitchin that sort of describes a general perspective on these sorts of things. So these kinds of results allow you to say that things like, in general, a negatively curved Riemannian manifold isn't going to admit Killing tensors, which is a negative result from the point of view of studying equations like this. It's saying that there's nothing interesting about them, but that it helps you to know where to look for interesting solutions. I should say all this is assuming Riemannian signature. In other signatures, I'm not aware. Probably for Killing tensors, there's quite a bit known, but for Codazzi tensors and other, there aren't even good obstructions in this sense known. And then if you want to actually prove something about solutions, the general philosophy is you go through, you have a sort of Laplacian associated to this operator A, this generalized gradient, and you obtain from it a Weizenbach formula for the coupled tensor omega. And so these have the form of the Laplacian of the tensor equals some curvature term applied to the tensor. And there's a general paper by Semmel and Weingart, which and also the older paper of Branson that I mentioned before, that give this general machinery and in just the way that's needed to apply to these equations. And the other ingredient that one needs are what are called refined Codazzi inequalities. And this is basically a Codazzi inequality bounds the norm squared of the covariant derivative of a tensor by the norm squared of the derivative of the norm of the tensor. And that such a inequality exists comes just from Cauchy-Schwarz. But when the tensor has specific symmetries and solves some equation like A is 0, usually you can improve the constant. And normally in improving the sort of results that I'll show in the next two slides, this is actually critical. And there's a general machinery for these generalized gradients that was Branson, Kauderbank, Gaudichon, Hertzlich, and there are a number of papers that describe this machinery. So you put all this machinery together, and what you get in general are things like a Laplacian of the norm squared of the tensor omega is related to some curvature terms. You get some sort of differential inequality, and depending on the signs, meaning the curvature signs and also this epsilon that is in all these equations, you either apply Chang-Yao style maximum principal arguments to obtain growth estimates, or you integrate it to get a Simon-style gap theorem. So let me say what I mean. So here's an example of so here I'm considering in the Codazzi case where I have a symmetric trace-free K tensor, which is Codazzi, divergence-free, and it solves this equation with this particular sign. Then one can prove these are the crudest things one can prove, but basically it's a bound on the norm of the, well, if this kappa is positive, then omega has to be 0, and the metric is actually a constant curvature metric, because that's what this equation says when omega is 0. But when kappa is negative, you get a bound on the norm squared of this tensor in terms of minus kappa. The bound, you can get a slightly better bound when k is 2 than when k is bigger than 3. And you can interpret this bound as actually a bound on the scalar curvature of the metric. What it says is the scalar curvature is non-positive. And when k is 2, it actually tells you the scalar curvature is negative, at least if the dimension is greater than 2. So for instance, this recovers some result about maximal space-like hypersurfaces in any de Sitter space due to Ishihara. Where I'm using this example. So the anti-de Sitter comes in, and you have the right sign here to apply this result. And when k is 3, in fact, you can prove something stronger. You can prove the same sort of result, but that the Ricci curvature is non-positive. And this is actually essentially due to Calabi in the context of hyperbolic affine spheres, which are known to have non-positive Ricci curvature. If we look at the other sign in this equation, so here I have a plus, you wind up getting, people call these gap theorems because in the k equals 2 cases goes back to James Simons in his paper on minimal hypersurfaces in spheres. And it's somehow, you think, just the way to understand this expression is it's quadratic in the scalar curvature, and it's got a negative sign here, so it opens like this. So it's somehow telling you that there's an interval where the scalar curvature can't fall in some sense. And when n is 3, this recovers a result of Chen, Oguyue in the case of Lagrangian submanifolds of Kähler manifolds, of mean curvature 0 Lagrangian submanifolds of Kähler manifolds. In general, I can prove the same result with some constant here. This isn't the right constant in particular, but there's something harder about the k bigger than 3 case. In part, it's maybe because we don't know what the geometric interpretation is. Okay, so now I want to, this is just a sort of summary of the general setup. It's just to say that one can say something about these equations. And what I want to pass to now is a very specific case of the differential geometry of hypersurfaces in flat affine space. And I want to explain what the preceding has to do with it and how it suggests interesting things to study in this context. So I'm going to quickly review the very basics of affine differential geometry, because they're not everybody studies this, knows this. And so I want to think of a co-oriented, non-degenerate immersed hypersurface in a manifold affine connection to start with, and I'm going to show that it has a conformal structure. The terminology co-oriented means the orientation of the normal bundle, so it has two sides. And non-degenerate, it means the non-degeneracy of the second fundamental form. So the second fundamental form is a normal bundle valued symmetric two tensor. You just take two tangential vector fields, you take the covariant derivative in the ambient connection of one along the other, and you project onto the normal bundle. And so it's not degenerate if this is a non-degenerate tensor. That makes sense because of the co-orientation. And if I pick a transversal, then it determines a genuine symmetric two tensor that in some sense represents the second fundamental form and a connection in just the usual way. And so basically the choice of transversal trivializes the normal bundle. And so you can write the second fundamental form like this. If I change the transversal, so here Z or Z is a tangential vector field. F is a non-vanishing function. So I think of it as scaling and changing the direction. The induced metric here rescales, and the connection somehow changes only in a way that doesn't depend on the scaling part. It only depends on the translational part. And so in particular, if my manifold is co-oriented, that means that I can choose these F's to always be positive, so that the W's are always consistent with the co-orientation. Then I actually get a conformal structure on the submanifold. If I suppose that the ambient manifold has a parallel volume density, then in fact I can get a distinguished metric here, at least up to homothenity, because if I have a parallel volume density on the ambient manifold, it determines two different volume densities on the submanifold. One is the volume density determined by the associated metric, and the other is the volume density obtained directly by interior multiplying the transversal and the volume density on the ambient manifold. And but requiring these to be equal determines a distinguished metric here. I say it really determines a homothenity class of metric because somehow the parallel volume density is also only determined up to homothenity, up to multiplying by a constant. But this metric usually gets called the Blaschke metric or the equiaffine metric. Okay, so now what I want to talk about is there are also a pair of connections that are somehow canonically determined on the submanifold, and let's see just how they're defined. So the first is I have a canonical choice of transversal, which is called the affine normal, really a canonical direction, affine normal line bundle. And it's easy to define in the convex case. So let me do that geometrically. In the convex case, I have a convex hypersurface. I pick a point. The tangent plane at that point lies on one side of the hypersurface. That's what convexity means. I can consider parallel translates to that tangent plane. They cut the surface in convex domains. I consider the curve formed by the barycenter of those convex domains. It passes through my initial point, and the tangent to it at that point is the affine normal line. So this is the original definition that Blaschke gave, and it's not very operative in the sense that one has to work a little bit to get out formulas from this definition, but it's conceptually very clear. It also doesn't work in other signatures. On the next slide, I'll show you how to define it in general. But I think if you remember one thing from this talk, maybe that's the thing to remember if you've never seen affine geometry before. So it depends on, if you write the hypersurface as a graph of a function, it depends on the third derivative of the function. And so once you have this affine normal, because here this change doesn't depend on the scaling here, really it only depends on the span of W, I get a canonical connection on the hypersurface. It doesn't have a standard name, but If my ambient space is actually flat affine space, I get a second canonical connection, or really a projective structure. And the way I get it is via what goes by the name of the conormal Gauss map. I associate to a point of the hypersurface the annihilator of its tangent space, viewed as an element of the projectivization of the vector space dual to the ambient flat affine space. It's easy to check that this map is an immersion if and only if the hypersurface has non-degenerate second fundamental form. In that case, I can pull the flat projective structure on this projective space back via the conormal Gauss map to get a flat projective structure on the manifold. And as I'll explain in a moment, there's actually a distinguished representative of this projective structure. So I really am going to get a pair of connections here. So in indefinite signature to define the affine normal, here's a way to define it. If you have any projective structure, any conformal structure, so I'm thinking of the conformal structure on the hypersurface in this one, for instance, but you can prove there's a unique connection representing the projective structure that I call it aligned with respect to the conformal structure, determined by this condition on the traces of the covariant derivative. The way to understand this condition is I look at the inverse metric and I multiply it by a term to make it. This doesn't depend on the choice of the metric within the conformal class. That's the point. And I require that this tensor be divergence free. That's really what I'm doing. And that determines a unique representative. And so the affine normal line bundle is determined essentially by this condition. It's to say, if I go back here and I vary the direction of W, the induced connection changes. And there's a unique choice of W up to its span that satisfies this condition. And so that singles out the affine normal line bundle. So it's well defined in general. So let me try to summarize all this structure. And there's a little extra information on this slide that wasn't present in what I just said. But the summary is that a co-oriented non-degenerate hypersurface in flat affine space acquires a pair of conjugate special statistical structures, one of which is projectively flat. So it's this last statement, which is what is special about hypersurfaces in flat affine space. So this terminology of statistical structure means a connection and a metric, so that this skew symmetrization in the first two indices of the covariant derivative vanishes. And special means that the determinant of the metric is parallel. So those two conditions can be summarized as saying that the covariant derivative of the metric is symmetric and trace-free. These structures sometimes are called Codazzi structures. There are other terminologies in the literature. I personally hate this terminology of statistical structures, but it's become quite popular. And it's a little bit like when people like to put quantum in front of everything. It makes no sense, but I've surrendered. And then there's a built-in notion of conjugacy, an evaluative notion of conjugacy. If I have one such structure, I can define a second one. This tensor is, I raise the third index using the metric. Now I have something that is a difference tensor type. So I add it to the original connection. I get a second connection that also constitutes with the metric a special statistical structure, and its cubic form has the opposite sign. So this is an evaluative notion in the sense that if I do it twice, I get back where I started. And the notations have been chosen so that in the previous slides, these are the same structures as before. It's to say, back here, if I take the aligned representative of this flat projective structure, it's the conjugate connection to the one induced via the affine normal with respect to the Blaschke metric. So that's what's summarized here. There's a little bit extra information here, but in the case of a non-degenerate hypersurface in flat affine space, I get a pair of special statistical structures. This is H is the Blaschke metric. Nabla is the connection induced via the affine normal, and this is the aligned representative of the flat projective structure induced via the conormal Gauss map. And it's worth noticing that the Levi-Civita connection of the metric, it lies halfway in between these two. In other words, I have Nabla bar, and halfway in between I have the Levi-Civita connection. And the statement that one of them is projectively flat, that is equivalent actually to these structures arising from an affine hypersurface. So in general, if neither of them is projectively flat, then this pair of structures does not come from an affine hypersurface. So I want to define Einstein-like equations for these structures. And so let me just say something really quick about the curvature. So you have the curvature of each of the two connections. I put a bar over it. And the summary is right here. So I'll say that it has self-conjugate curvature if the curvature tensor of nabla is equal to the curvature tensor of the conjugate connection. And the summary of this calculation below is just that the difference of these two curvature tensors is given by the Codazzi operator applied to the cubic form, the covariant derivative of the metric. And that means that the curvature is self-conjugate if and only if this cubic form is Codazzi. And a slightly weaker statement is the Ricci curvature is self-conjugate if and only if this cubic form is divergence-free. The proof, this is an indication. You take the second derivative of the metric, you skew symmetrize, you use the Ricci identity, you get out this thing here that's symmetric in K and L. On the other hand, you calculate a bit and you get out the Codazzi operator applied to the cubic form. And you combine everything and you get this. Okay. And I've noted here the relation of, so R is the curvature tensor of nabla, Riem, Rick are the curvature tensor of the Levi-Civita connection of the metric. What I want to observe here is they're the same, except, well, I have these two terms which are going to vanish when my cubic form is opposed to Codazzi, and then I have these terms that are the Kulkarni-Uemitsu product of L with itself and its Ricci trace. So this all started with trying to define Einstein equations in this context. And the upshot is going to be that I need the Codazzi condition to get a good idea. That somehow the naive thing is to say something like, well, let's take our special statistical structure. Let's try to make an Einstein definition that at least respects conjugacy. I want the conjugate of an Einstein structure to also be conjugate, to also be Einstein. And so maybe I say that the Ricci tensors of both are multiples of H. Those are essentially all the possible Ricci type traces I can take. And this turns out to just be too weak a notion. And it also doesn't imply the constancy of the scalar curvature. So this equality is automatic, but the constancy does not follow from this condition above. Because when you go to how do you prove the constancy of the scalar curvature of an Einstein metric? You use the trace differential Bianchi identity. And in this case, you run into some terms that involve the Codazzi operator applied to the cubic form. So that somehow I tried for some time to work with this definition, but what one finds is, so it meets a certain consistency check, at least if my statistical structure is actually, the connection is the Levi-Civita connection, it gives me the usual Einstein equations. But what one finds is that this second condition follows from the first if I suppose that the cubic form is Codazzi. There's something slightly weaker. I can assume that the Weil part of the curvature tensor of nabla is self-conjugate. That's enough to get this. But I'm just going to make this stronger assumption right here. So really what I want to think about is this pair of equations, these Einstein equations here, plus the self-conjugacy of the curvature. And that turns out to be equivalent to these coupled Einstein equations that I defined before for H and L by themselves. And so that was the point of all that introduction before, is somehow this seems to me very natural, and I think therefore this is the correct natural notion in this particular context. And then when one thinks about the hierarchy of equations I wrote before, there's a projectively flat version, a stronger set of equations here that corresponds to these. And what it corresponds to on this side turns out to be exactly that the curvature tensor of nabla is a multiple of the metric. And so actually, if I consider this and I go back to these calculations here, it follows that implies that the curvature tensor of the conjugate connection is also a multiple of the metric, and it's the same multiple of the metric, so that in fact the curvature is self-conjugate. And so this assumption by itself is enough to prove that this cubic form is actually Codazzi, and then that with this equation here is enough to get out these equations. So somehow in this particular case, this hierarchy corresponds to these conditions. So this is nice because these equations have a good geometric interpretation. And the good geometric, so I'll define what an affine sphere is on the next slide, but let me just say this first for those who already know what affine spheres are. So I'll define it here, but I'll explain examples. An affine sphere is an affine hypersurface whose affine normals all meet in a point or all are parallel. And so in the next slide, I'll explain how to think about them. But the result here is that for a hypersurface in flat affine space, the special statistical structures, these conditions are equivalent. The hypersurface is an affine sphere. These induced structures have self-conjugate curvature. They're Einstein in the sense of the preceding slide. And it actually turns out, at least when n is bigger than 2, this is the same as assuming that they're both projectively flat. So this actually, stated this way, it seems very restrictive, but so what in the convex case, affine spheres are well understood. There are 3 kinds. An affine sphere is elliptic if its center, which is where the affine normals meet, is contained on the side to which it curves. And in that case, if it's compact or if the Blaschke metric is complete even, it has to be an ellipsoid. And the metric is a constant curvature metric, and so it's not very interesting. It's a parabolic affine sphere in the convex case if the affine normals are all parallel. And then this is a somewhat deeper theorem that in that case, it's necessarily an elliptic paraboloid if the metric is complete, if the Blaschke metric is complete. This is a fairly, I probably should put I think Pogarov also proved this. Now that I think about it. So these are sort of negative results, but what turns out is that in the hyperbolic case, which is where the center is on the side away from which the hypersurface curves, there are many, many examples. So the way to think about this is think about the Minkowski cone. Its interior is foliated by hyperboloids. What this theorem says, this is a theorem of Cheng and Yao, is that if you take any pointed convex cone, so think of any convex domain whatsoever and the cone over it, then its interior is foliated by hyperbolic affine spheres that are asymptotic to the cone and whose center is at the vertex of the cone. And this is proved by solving some Monge-Ampère equation. It's sort of a real version of the Kähler-Einstein problem in negative scalar curvature. It's essentially the same at a technical level. And this shows that there are a lot of affine spheres. This condition defining affine spheres, you can also think of it as the shape operator is a multiple of the identity. The shape operator defined in terms of the affine normal. And so these are the umbilic objects in affine geometry. In the non-convex case, there's no real systematic study, no theorems of the quality of these theorems. These obviously used in a very strong way, sort of elliptic PDE techniques. And so it's a totally different world when you go to other signatures. There are lots of examples. I built some from relative invariance of irreducible pre-homogeneous vector spaces. This gives you some examples you can write down quite explicitly. And then both I and Roland Hildebrand wrote down a bunch of examples using different kinds of constructions from non-associative algebras. Roland also wrote down some explicit examples of the Cheng-Yao theorem. In other words, for specific cones, he can write down formulas. He's actually written quite a bit about this kind of thing. I'm going to skip this slide. And so there's a remaining question. So I have some equations which I claim are kind of nice, these ones. And I'm claiming that their solutions have this geometric interpretation as affine spheres. But I have a further question is, are there examples that don't arise in this way? Okay. And so in the last couple of slides, I'm just going to quickly say how to get such examples from a purely algebraic construction. And this I'm going to try to summarize this. The idea is to think of a flat background metric, and a parallel cubic form. It's to say that this tensor is parallel. And I want to view this then as the structured tensor by raising the last index of a commutative and general non-associative multiplication. And so here I have a commutative algebra. I just made a bilinear multiplication. I'm going to speak of a metric as a non-degenerate symmetric bilinear form. This L is just add in the context of Lie algebras. It's the left multiplication endomorphism, and it's essentially equivalent data to the structure tensor. And I'm going to call my algebra exact if the traces of the left multiplication endomorphisms vanish. This corresponds to this trace-free condition on the structure tensor. And I'm going to call the algebra metrized if this trilinear form constructed from the multiplication of the metric is completely symmetric, which corresponds to this condition on the structure tensor. So you should think of this as like the invariance of the Killing form with respect to the invariance of the Killing form on a Lie algebra. It's the analog for commutative algebras. And this is the analog for commutative algebra, the unimodularity of a Lie algebra. And okay, so we just quickly. I'm almost finished. I'll stop. So I'll call the metric the algebra is Killing metrized if this Killing form, and this is if you think add, this is the Killing form for a Lie algebra, is an invariant metric. And I have the associator, which I should think of as the commutativity of these left multiplication endomorphisms. That's using the commutativity of the algebra. And let's call it projectively associative if this tensor is somehow a pure trace. And so I can write all this in terms of the Kulkarni no Mitsu square of the cubic form. So that should be this cursive L, really. But and I get expressions. So I can build then from H and L the associated nabla, and I can write down its curvature. And these look very much like formulas that one is familiar with from Lie algebra context. And the upshot is that such an algebra, this pair is coupled projectively flat or coupled Einstein if and only if this algebra satisfies this projectively associative condition or it's Killing metrized. So these are two tractable algebraic conditions, and there's just two more slides and I'll stop. Okay. So the first is that I can completely classify the solutions to this equation, because what really interests me are solutions to this equation that don't solve this equation. Because I want solutions to this equation that aren't solutions to this equation. So there's some algebra that was on the standard representation of the symmetric group on n+1 elements, which is given this way. It's a commutative algebra with this product, which was first studied by Griess and Harada a long time ago. And the theorem is that here, what matters is over R. This algebra is exact, Killing metrized, projectively associative. And any such algebra, any exact Killing metrized, projectively associative algebra is isomorphic to this algebra. So I have what the utility of this theorem in the context of the present talk is that if I have a Killing metrized algebra, not isomorphic to this algebra, whatever this algebra is, then it gives me an example of a solution to these equations that's not a solution to these equations. So the last comment is there are a lot of such algebras. They're quite interesting ones. The most famous and most interesting example is that Griess constructed the monster finite simple group as the group of automorphisms of a simple, exact, large algebra, commutative algebra, which can be proved to be Killing metrized using calculations made by Titz and Conway. And so it actually satisfies this condition, although it does not satisfy this condition. And on the final slide I just listed, there are actually a bunch more examples and some classification results. But I've already run over by a couple minutes, so I will stop. And
yeah, thank you very much for this talk. Are there any questions or remarks? Yes, please.
General algebraic setup. At the very beginning, you had this slide about general scheme. So you said that you have a pair of W symmetric values in K, which you will curvature tensor. Right? So algebraically, I mean.
here, yeah.
So what is K algebraically? Can you say
K is it's the K here is just the square with 4 boxes. It's algebraic curvature tensors.